Welcome to the World Energy Engineering Congress. My name is John Fetters. I'll be chairing the session, and the session is the Energy Basics Track E, Session E2, the basics of dimming LED bulbs and SSL, solid state lighting fixtures. So welcome to the session. We'll start with Tanya. Thank you.
Good morning. Okay, my name is Tanya Hernandez, and I'm actually one of the presenters, but I'm actually here at this very moment to introduce our first speaker, who you just heard from, but you don't know much about him, so I will fill you in. So John Fetters is an accomplished electronics engineer with a special expertise in energy-effective lighting. He received his electronics engineering degree from Cleveland State University and an energy management diploma from the University of Wisconsin. He's a certified energy manager, a certified lighting efficiency professional, and a certified energy auditor. John is a member of the IES Illuminating Engineers Society and is currently a member of the Visual Effects of Lamp Spectral Distribution Committee and an advisory member of the Industrial Lighting Committee. So John's presented so many seminars and technical presentation sessions at major conferences. This is my second go round with him, including the Energy Education, Energy Exchange, which is formerly known as Gov Energy, at Light Fair International, NAMCO conferences, and of course here at WEEC. He's been a regular guest lecturer for the University of Wisconsin, teaching the lighting sections of fundamentals of energy auditing and engineer professional development courses, and he currently teaches performing building lighting audits, getting ready for LEDs and solid state lighting. He recently completed 4 video modules for Synergistic for use in their in-house online training. So John is an approved instructor in the Building Operator Certification Program, and he teaches a course BOC 1003, which is the basics of energy efficient lighting. So next speaker is John Fetters.
Thank you, Tanya. When I put this program together last year, I didn't realize that dimming would still be an issue. I should have guessed, I guess, but we've got challenges, and I thought you'd like to hear from some people about different perspectives about dimming, because it is still a challenge. We can start with some dictionary definitions. When you look up dimming in the dictionary, what you find is something not very helpful, lacking in brightness. Another definition I found was emitting only a small amount of light. If you go to the definition for dimmable, you find able to be dimmed, able to have illumination decreased in brightness. And then the definition for dimmer, a device for varying the brightness of an electric light, or a device that allows you to control the brightness of a light. Those aren't very helpful definitions. Let's start with some dimming basics. All dimmers will save energy and extend lamp life. Each type of lighting source has individual characteristics that require special types of dimmers. We have a lot of different types. I've put a few of them up here. First of all, the incandescent halogen. Line voltage, 120 volts, tungsten filament lamps present a resistive load and require a rheostat, which is the old technology, or forward phase control, which is the newer electronic control. We have magnetic low voltage MLB. Those are for the magnetic core and coil toroidal toroidal, always had trouble with that name, transformer supplied low voltage lighting, 6, 12, or 24 volts. And they present an inductive load and require symmetric forward phase control. Electronic low voltage, ELV, solid state transformer supplied low voltage lighting presents a capacitive load and requires reverse phase control to provide very smooth turn on and a neutral wire connection. It's a myth that dimming does not save energy. Back when we did dimming with rheostats, I'm not that old, but I have seen some old rheostats. We did not save energy because you either consume power in the rheostat or you put the power in the lamp. Dimming's now done with solid-state dimmers that do save energy, and it's done by variable power conduction. Yes, I know you have adjustable resistor on the wall, but it's not a rheostat. It's a variable power conductor. It's you able to set the phase, where in the phase it's going to cut the power. So therefore, it's called either phase cut or wave chopping. So here's an old rheostat I found a picture of. These are obsolete, so we really need to change our vocabulary. We now use electronic dimmers to save energy and extend incandescent lamp life. Dimming control, we have the square law of dimming. Our visual response, human visual response, is not linear. It looks linear in the upper part of the curve, but notice down at the low end, it goes very nonlinear. So here we see the percent of light measured on the vertical axis and the percent light perceived by the eye on the horizontal. So the light measured varies as the square of the perceived light, or you could say the perceived light varies as the square root of the measured light. And most dimming is going to occur down at the low end, below 10%. For example, to achieve a space that appears half as bright, the lighting system output must be reduced by approximately 32%, and for 1/10 of a perceived brightness to approximately 2% of full light output. Now, we have used this curve for incandescent lamps to show the effect of voltage on incandescent lamps. We notice that as we reduce the percent of rated voltage applied to the lamp, the lumens will go down, the watts will go down. Now the curve does not end at the left here, it keeps going, and we see the life goes up. So as we get lower and lower, the lumens go down, the watts go down, the life goes up. So some dimmer considerations. Heat dissipation. Dimmers get warm during normal operation. The Wallbox dimmer efficiency is about 99%. The other 1% is dissipated by heat. When we operate the dimmer at their rated load, the dimmers are required to stay below the UL limit of 140 degrees F. When you gang dimmers together, you have to have some considerations here, because a typical dimmer is wider than a switch to help dissipate the internal heat. When you gang those dimmers together, you have to take part of the heat fins, the heat sink must be removed. So when you do that, it removes the wattage capacity and each dimmer can control. Now, when you start applying dimming or dimmers to LED lamps, we still have the light output proportional to the power. Some of the LED lamps are going to require an ELV. Remember we showed that one earlier, electronic low voltage type of dimmer. Dimmer will extend LED life. The LEDs run cooler. But we have some, I put some, maybe I should have put a lot, of compatibility issues. The dimmer must be matched to the LED lamp. And you have to investigate that for your application. So you can go to control company websites like the Lutron website and find tables of compatible dimmers, ones that have been tested with LEDs. Now, there's a very important point here. It's the last one on here, but it's the most important thing on the slide. We used to know how to use dimmers that were rated like 600 watts. You just added up the loads and make sure they didn't exceed 600 watts. You can't do that with LEDs. There's an inrush current that set by the capacitors in the power supply of each of the LED bulbs that causes an inrush current. And that inrush current is what's going to set the maximum number of lamps on a dimmer, not the wattage rating of the dimmer. So that's very important. We have a couple of different dimming standards that we can download for free from the NEMA website. That's the National Electrical Manufacturers Association. There was one, an LSD 60, the effects of dimming on color and efficacy of LED lamps. I've given you the website there. Energy savings with fluorescent and LED dimming, published in July of 2015, is NEMA LSD 73-2015, and that's also a free download at that website. Flicker is caused when we have wave chopping dimmers when they're used with LEDs. Now, this is time without power. If you look at this forward phase control, you see that you get the control allows you to adjust to turn on the waveform at this point. It turns off at zero crossing and then turns back on here. In the reverse ELV type phase control, it's done on the trailing edge. But anytime we have time without power, that's going to cause us flicker. Now, flicker in LED luminaires is an important consideration. There was a report written by Terry Clark, the chairman and chief technology officer of Fine Light, and he wrote this paper a couple years ago, Flicker in LED luminaires. The presence of flicker in LED lighting applications is dependent on the light modulation characteristics of the LED driver. There's two types of LED drivers to choose from: pulse width modulation and constant current reduction. You're going to hear that several times today. The pulse width modulation drivers dim by rapidly switching the current to the LEDs on and off. The ratio of the time on to the time off determines the perceived brightness. When they're dimmed, flicker can become apparent. The other type we have is a constant current driver. We dim that by reducing the amount of current delivered to the LEDs. The LEDs do not turn off and on. We may see ripple on the output current signal that's there, whether it's full on or whether it's dimmed. So, whether we use pulse width modulation or constant current really depends on the application. The applications suitable for PWM are fixtures that must be dimmed lower than 40% and still maintain consistent color. Another application is color mixing applications because of their need for precise levels of each color. Other applications suitable for CCR are fixtures requiring a UL Class 2 rated output with an output voltage higher than the UL Class 2 PWM voltage level. Applications where long wire runs may exist between the driver and the light engines and high performance dimming is required. Other applications that may have very strict EMI, electromagnetic interference requirements, such as medical suites, and applications with high motion activity or rotating machinery. In the Fine Light Flicker report, it describes 4 ways to check flicker in LED drivers. If you're an electronics engineer, just get out your waveform analyzer and you can observe the exact wave shape. Other ways, where you're not an engineer, maybe a flicker checker. We used to have these Motorola flicker checkers that I still have them. I suppose some people also have them maybe in their closet. but you can use that to observe the visible pattern. If you see a choppy, distinct pattern, that means there's a high degree of flicker present. If you see, on the other hand, the photo on the right, you get smooth concentric circles, and that means there's minimal flicker present. You could wave an object under the light source to see if you have multiple images. For example, a pencil, as shown here. Probably the best way for us to check flicker is to mock up the space with all the sources and dimmers to experience firsthand what we're going to see. The report also describes 4 ways to measure level of flicker. There's a DOE report on dimming, caliper testing, the program from the DOE, and the gateway demonstrations are showing dimming of LEDs is still a challenge, especially with compatibility. Dimming LEDs with phase-cut dimmers is a report subtitled The Specifier's Process for Maximizing Success, and the report offers general guidance. It's intended to reduce the likelihood of compatibility-related dimming problems. It also provides you specific step-by-step procedures for designing phase-controlled LED dimming on new and existing projects. Examples were from the Gateway demonstration at the Bourdain Museum in Troy, New York, which just happens to be the home of the Lighting Research Center at Rensselaer. And quoting from the report, excellent quality LED dimming with phase control dimmers can be achieved, but, okay, see, big but, all caps, but requires dimming mock-ups or diligent research into compatibility. And it summarizes the report: with time, LED sources, their components, and dimming systems will evolve and improve. But until then, this report can serve as a useful reference. I've given that website address there so that you can go to there and get that, download that report.